On September 15th, 2017, a spacecraft that had spent 13 years quietly orbiting Saturn deliberately flew straight into the planet and destroyed itself. It wasn't an accident, it wasn't a malfunction. NASA planned the entire thing on purpose, down to the final second. And in those final moments, as the spacecraft burned apart in Saturn's atmosphere, it kept transmitting data back to Earth for as long as it possibly could. Some of what came back in those last transmissions is still being studied today, and at least one mystery buried in that data remains genuinely unsolved, years after the spacecraft itself stopped existing. Stay with me, because this isn't some exaggerated internet rumor. This is real, published, peer-reviewed science, and the story behind Cassini's final dive is stranger than most people realize. To understand why Cassini ended the way it did, you have to understand what it had already accomplished by that point. The spacecraft launched on October 15th, 1997, and entered orbit around Saturn on June 30th, 2004, carrying with it the Europeans' Huygens probe, which would later make a historic landing on the Moon Titan, becoming the first spacecraft ever to touch down on a world in the outer solar system. Over the following 13 years, Cassini completed nearly 300 orbits of Saturn, captured more than 450,000 images, and sent back roughly 635 gigabytes of scientific data. Along the way, it delivered some of the most important discoveries in the history of planetary science, including strong evidence for a global subsurface ocean on the Moon Enceladus, complete with signs of active hydrothermal activity and confirmation of liquid methane seas sitting on the surface of Titan, a moon with weather and geography eerily reminiscent of Earth, just built out of completely different chemistry. What was originally planned as a 4-year primary mission ended up stretching across 2 full decades, extended twice as the spacecraft kept proving itself capable of far more than anyone had originally expected when it first launched. By 2017, though, Cassini was running dangerously low on fuel, and that created a serious problem. Without enough propellant left to reliably control the spacecraft, mission planners couldn't guarantee they'd be able to prevent it from eventually drifting into an uncontrolled collision with one of Saturn's moons, particularly Enceladus or Titan, both of which are considered genuinely promising locations in the search for life elsewhere in the solar system. Even though Cassini had been carefully cleaned before launch, there was still some small risk that Earth microbes might have survived the journey, hitching a ride on the spacecraft for 2 decades. If Cassini eventually crashed into one of those potentially habitable moons, uncontrolled, there was a real chance, however small, of contaminating an environment that scientists are still actively trying to study for genuine signs of life. So NASA made a deliberate decision. Rather than risk that outcome, they would use Cassini's last remaining fuel to send it on one final dramatic mission, then plunge it directly into Saturn itself, where it would burn up completely and pose no further risk to anything. That final chapter became known as the grand finale, and it turned into something considerably more interesting than a simple planned demolition of an aging spacecraft. Starting in April of 2017, Cassini began a series of 22 increasingly daring dives, threading itself directly through the narrow gap between Saturn's cloud tops and its innermost ring, a region roughly 2,400 kilometers wide that no spacecraft had ever dared enter before. Nobody was entirely certain the spacecraft would survive even the first of these passes. Mission scientists genuinely worried that ring particles and debris in that gap might collide with Cassini at extreme velocity and destroy it early, cutting the whole plan short before it even really began, potentially ending the mission on the very first attempt, rather than after 22 carefully planned dives. But the risk paid off. Orbit after orbit, Cassini successfully threaded that narrow gap, gathering close-up data that simply wasn't possible to collect any earlier in the mission, when getting this close to the planet would have been considered far too dangerous to attempt. Then, on the morning of September 15th, 2017, Cassini made its final approach. It stopped storing data locally and instead began streaming everything directly back to Earth in close to real time with only a few seconds of delay, specifically so that as much science as possible could be recovered even if the spacecraft was destroyed moments after transmitting. With 8 of its scientific instruments still actively running, Cassini plunged into Saturn's thick atmosphere at a staggering 76,000 miles per hour. Mission director Earl Mays put it bluntly at the time: there was absolutely no coming out of this particular dive. The spacecraft was going in far too deep for any chance of survival. As it fell, Cassini kept gathering data for as long as it physically could, measuring the ratio of hydrogen to helium in Saturn's atmosphere and identifying trace chemicals that scientists have no way of measuring accurately from Earth-based telescopes alone. And then, finally, the signal stopped. Cassini's transmitter lost its lock on Earth as atmospheric forces tore the spacecraft apart, and it burned up completely, scattering across Saturn's upper atmosphere like an artificial meteor. Even those final seconds of transmitted data turned out to carry genuinely unique scientific information about Saturn's atmosphere, information that simply couldn't have been gathered any other way, from any other vantage point, using any instrument currently available to humanity. But the real scientific payoff from the grand finale wasn't limited only to those last few seconds. It came from the entire 6-month sequence of daring, close-in dives that led up to that final plunge, and some of what scientists found during that stretch turned out to be significantly stranger than anyone had originally expected. One of the most surprising discoveries involved the region directly between Saturn and its rings, the exact gap Cassini had been threading itself through during those final orbits. For roughly 40 years before the grand finale, scientists had relied entirely on remote observations and theoretical calculations to understand how material moved from Saturn's rings down into the planet's atmosphere. The leading model assumed that Saturn's magnetic field was primarily responsible, carrying charged ions and dust particles from the rings toward the planet's mid-latitudes in a fairly orderly, predictable process. But once Cassini actually flew directly through that gap and took real direct measurements for the very first time, scientists found something they hadn't fully anticipated. Alongside the expected magnetically guided material, there was also a completely separate stream of extremely fast-moving molecules and particles, some smaller than 2 nanometers across, flowing directly along the plane of the rings and into Saturn's atmosphere through simple atmospheric drag, a mechanism nobody had properly accounted for at that scale. Researchers ended up describing it informally as a kind of ring rain, constant material raining down from the rings into the planet through more than one physical process happening simultaneously, a picture considerably more complicated than the clean, single mechanism model scientists had worked with for decades beforehand. That wasn't the only surprise, hiding in that supposedly empty gap between the rings and the planet. Cassini's instruments also picked up direct evidence of complex chemical interactions happening in that narrow region, interactions that turned out to be considerably messier and harder to fully explain than researchers had originally predicted. Close-up observations of the rings themselves added even more unresolved questions to the pile. Scientists studying detailed images from these final orbits noticed patchy, clumpy structures in the main rings, informally nicknamed straw, that Cassini had actually glimpsed hints of earlier in the mission as well. But the higher quality images gathered during the grand finale made something clear. That clumpy texture didn't line up neatly with the existing pattern of ring structure, and it didn't correlate cleanly with any of the known gravitationally induced wave patterns already mapped out within the rings either. Researchers directly involved in studying these images have been open about the fact that they simply can't yet fully explain how or why this particular clumping pattern forms. Then there's a mystery that reaches even further than the rings themselves, one that researchers working on the grand finale specifically hoped this mission phase might finally resolve, and one that, even now, largely remains unsolved. It concerns something surprisingly fundamental: exactly how fast Saturn actually spins. That might sound like an oddly basic question for a planet humanity has been observing carefully for centuries, but Saturn's thick, swirling atmosphere makes it essentially impossible to simply watch a fixed surface feature and time its rotation the way you could with a rocky planet like Mars. Instead, scientists typically try to measure a planet's true internal rotation rate using its magnetic field, since a planet's magnetic field is generated deep in its interior and should, in theory, rotate in lockstep with the solid or metallic material actually producing it. For that method to work cleanly, though, scientists need to detect at least a slight tilt in the planet's magnetic axis relative to its rotational axis, since a perfectly aligned magnetic field provides no usable timing signal to actually lock onto. Every other planet in the solar system that's been carefully measured shows at least some detectable tilt of this kind. Saturn stubbornly does not. Cassini's grand finale orbits were specifically designed, in part, to get close enough to Saturn to finally detect even the smallest possible tilt in its magnetic field, fine enough to nail down the planet's true rotation rate once and for all. Researchers working on the mission's magnetometer instrument went into the grand finale, hopeful that this final, extremely close set of measurements would finally crack the problem open. According to planetary scientists directly involved in this research, the results left them more puzzled rather than less. As one researcher studying the data put it directly, people are genuinely perplexed by the fact that they still can't identify any meaningful tilt to Saturn's magnetic dipole. Even now, even with this unprecedented, extremely close-range data in hand, that same researcher went on to call it one of the biggest open mysteries left in planetary science today. Think about what that actually means for a moment. We sent a spacecraft on a 2-decade journey, deliberately risked destroying it early by threading it through a genuinely dangerous gap between a planet and its rings, specifically hoping to finally pin down something as basic as how long a single day lasts on Saturn. And even with all of that effort, all of that risk, and all of that remarkably close-range data, The fundamental measurement scientists needed still wasn't cleanly there in the numbers. Saturn's magnetic field remains stubbornly, almost suspiciously well aligned with its rotational axis, far more precisely aligned than current theoretical models of how planetary magnetic fields form can comfortably explain. Some researchers have proposed that unusual atmospheric dynamics deep inside Saturn, involving layers of helium rain falling through the planet's interior, might somehow be smoothing out or masking any underlying tilt before it ever becomes detectable from the outside. But that remains a proposed explanation rather than a confirmed one. And Saturn's precise rotation period is still, even today, not pinned down with the same confidence scientists have for essentially every other planet in the solar system. It's worth appreciating just how strange this particular gap in our knowledge really is, especially given everything else Cassini managed to measure with remarkable precision during its mission. We have extremely detailed maps of Saturn's gravity field. We have precise measurements of its ring structure, down to individual clumps of material only a few kilometers across. We have detailed chemical breakdowns of its atmosphere, gathered directly during those final fiery seconds before the spacecraft was destroyed. And yet, something as conceptually simple as how long is one day on Saturn remains stubbornly out of reach, not because nobody has tried hard enough to measure it, but because the planet itself seems to be actively hiding the one signal scientists need in order to calculate it cleanly. That's part of what makes this particular mystery so compelling to researchers who've spent years working on it. It's not a case of insufficient data or insufficient effort. Cassini gathered about as close and as precise a set of measurements as any spacecraft reasonably could, specifically targeting this exact problem during its riskiest, most dangerous orbits. The problem isn't a lack of trying. It's that Saturn's interior appears to be doing something genuinely unusual, something current models don't fully account for, that keeps this particular measurement locked away from us. There's an interesting contrast worth mentioning here, because not every mystery uncovered during the grand finale has remained unsolved. Roughly 3 years after Cassini's final plunge, a separate research team used the mission's gravity and temperature mapping data specifically gathered during those final close orbits to help resolve a long-standing puzzle known as Saturn's energy crisis, a mismatch between how much energy models predicted the planet should be radiating and how much it actually appeared to be giving off. That particular mystery saw real meaningful progress using grand finale data, published years after Cassini itself had already been destroyed. It's a good reminder of how deep space missions like this one keep generating. New scientific results long after the spacecraft responsible for gathering the data has already been gone for years. The rotation and magnetic tilt problem, though, has proven considerably more stubborn and remains open territory for researchers still actively working with Cassini's archived dataset today. There's also the matter of Saturn's rings themselves, and just how old they actually are, another question the grand finale was specifically designed to help settle. During its closest passes, Cassini broadcast a precise radio signal back to Earth while skimming near the dense B ring, the thickest and most opaque of Saturn's main rings, one so dense that light can barely pass through it, making its total mass extremely difficult to measure using ordinary observation methods alone. The idea was that the ring's gravitational pull would cause extremely small, precisely measurable shifts in the wavelength of that radio signal, letting scientists calculate the ring's true mass directly. That measurement matters enormously because the total mass of Saturn's rings is closely tied to an ongoing debate about their actual age. Some models suggest the rings are genuinely ancient, having formed alongside Saturn itself more than 4 billion years ago. Other models suggest something considerably stranger, that the rings might actually be quite young by astronomical standards, possibly forming within only the last 100 million years or so, meaning dinosaurs could theoretically have been walking around on Earth before Saturn even had its now iconic rings at all. Grand finale data helped narrow this question down considerably, though even now, refining exactly how and when the rings formed remains an active area of ongoing research built directly on measurements Cassini only became capable of taking during its very final, riskiest orbits. So, when you put the entire picture together, Cassini's ending wasn't simply a dramatic, cinematic finale designed purely for the history books. It was a genuinely productive, extremely high-risk final phase of science that produced real, measurable, peer-reviewed results, some resolved, some still stubbornly unresolved even years later. The spacecraft threaded a genuinely dangerous gap 2 separate times, successfully gathered direct measurements of processes scientists had previously only been able to theorize about from a distance, and then, in its absolute final moments, kept transmitting hard data back to Earth for as long as its small thrusters could physically keep its antenna pointed home, right up until atmospheric forces finally tore it apart completely. And buried somewhere in that final flood of information sits a genuinely open scientific mystery. Saturn's magnetic field still won't reveal the tilt scientists need to finally pin down exactly how fast the planet spins, despite one of the most ambitious, most dangerous data gathering campaigns ever attempted specifically to solve that single problem. Researchers are still actively working with Cassini's archived data today, still testing new theoretical models, still trying to explain why this particular measurement continues to resist every method thrown at it so far. It's a genuinely rare kind of scientific story, one where a mission's spectacular, deliberate act of self-destruction ended up generating more open questions in certain areas than it managed to close, even while resolving other long-standing mysteries entirely along the way. If stories like this, ones where real, hard data still leaves genuine scientific mysteries sitting unresolved years later, are the kind of thing you find fascinating, make sure you're subscribed to this channel with notifications turned on, because researchers are still combing through Cassini's full archive today, and the next major finding pulled from that final flood of data might be the one that finally settles exactly how fast Saturn actually spins. There's something quietly poetic about how this particular story has unfolded so far. A spacecraft that no longer exists, destroyed deliberately on a September morning years ago, is still actively shaping planetary science today, simply because of how much data it managed to gather in its final, riskiest months of operation. Every so often, another research team pulls a fresh angle out of that same archived dataset, testing a new model, checking a new hypothesis, occasionally resolving a decades-old question, and occasionally deepening one instead. Cassini itself is gone, scattered as vapor and debris somewhere in Saturn's upper atmosphere, but the questions it left behind are still very much alive, still actively being worked on by scientists who never got to see the spacecraft fly. Using data gathered during its very last, most dangerous orbits around the planet, it spent 13 years quietly getting to know.